In the last lecture, we were talking about discrete convolution and continuous time convolution. So we looked at multiple approaches to determine the convolution output, which is essentially used to find the output of linear and time invariant systems. For the graphical approach, for the discrete convolution, we used three different ways. One was the analytical approach, then we also looked at graphical approach, and we had a much easier array-based algorithm to give us the discrete convolution result. For continuous time convolution, we looked at two approaches. One was the analytical approach, and one was the graphical approach. The graphical approach is the more general approach, and I would recommend you to do some really good practice with the graphical approach of continuous time convolution. And some of the homework 6 problems are pretty comprehensive, so they are intended to give you a lot of practice. I'm referring to problem 3 on homework 6 here. So I hope you guys pay special attention to that problem. Okay, so let's begin lecture 7, and the agenda that I have today is laid out on the first slide here. And depending on how much time we have left, we can go ahead, go beyond these topics. But I want to begin today with talking about discrete convolution in Matlab. So there's Matlab is a tool that has a function called conv that allows you to convolve two sequences. And if you can, and this is being done in the command prompt here, so you could write a MATLAB script and then fill in these MATLAB commands, or you can directly type them into the command line. So if you have a few statements to write, for example, over here you just have 4, so you could directly enter them into the command line, which is indicated by the 2 greater than signs here. So I've initialized x as a sequence of discrete variables 2, 1, 1, h as 1, 2, 3, and then y equals conv, which is the convolution operator, x comma h. I'm terminating these MATLAB statements with a semicolon so that they don't echo back the answer inside the command window. And then to sketch the output, I use the command plot, instead of plot, I use stem because it's a discrete function here. So plot allows you to do continuous signals because it connects the dots. Stem leaves them as is in a discrete manner. So the time axis is defined over here as 0 to 4, 5 elements, because 3 plus 3 minus 1 gives you 5. So 0 to 4 will take care of the 5 elements. And then you are sketching y on the y-axis. So this is one quick way to check your work. So if you're doing some convolutions, you can, after you actually do them mathematically on piece of paper, you could use MATLAB and these 4 statements to evaluate the convolution very, very quickly and even sketch it. Now, you might wonder, okay, so if I can do this for discrete time, can I also do this for continuous time? Well, continuous time, you are going to have to find a way in order to represent continuous time signals in a computer. And the only way to do that is by assuming that the sampling time is very, very, very small. So if you assume that the time between any two values is very small, then you can make an assumption that that is a continuous time signal. But again, it's going to be an approximation. So you could, in fact, say this. So let me do a separation here and say sampling time, say Ts equals, say, 1e minus 3, which is 1 millisecond. And that's my sampling time. So that's time interval between any two values. And I can form a time vector here, which goes from 0 to, for example, 5 in the steps of 1 millisecond, TS. And then I can define my x as some function of x, some function of time. And I can also do that for h. I'm not writing the specific things here. I will leave that to you. So some function of time for x and h. And similarly, you can write down y as convolution of x comma h, or h comma x, doesn't really matter, it's commutative. And then you can say plot t comma y. So in this case, you use plot because you want all those samples to get connected so that they appear continuous. But again, this is based on a sampling granularity of 1 millisecond. You can go even lower than that. If you do, instead of having 5001 values in the time vector, you're going to have much more than that. So you could use these strategies to validate your convolution work. This is being presented to you not as a means of finding the convolution, but as a means of validating your work. So I hope you find that helpful. This is as far as Matlab convolution is concerned, for both continuous and discrete. In discrete, you're actually doing it the way it is supposed to. In continuous, you are sort of approximating things by picking out a very, very small sampling time of 1 millisecond in this case. Next, while we were talking about discrete convolution, one way of understanding discrete convolution is by looking at it as a multiplication operation between two polynomials. So if I define a polynomial in x as a2x squared plus a1x plus a0, a0, a1, a2 are coefficients of the constant x and x squared respectively. And similarly, I have q of x, another polynomial in x. In both these polynomials, it's going up to a quadratic. I have b2x squared plus b1x plus b0. Now, if I multiply these two polynomials, p and q, I will have the fourth power polynomial as a result. So x to the 4 all the way to the constant. Now, if I define the coefficients of x to the 4, x cubed, x squared, as c sub 4, c3, c2, c1, and c0, then notice what happens when you calculate c2. c2 is the coefficient of x squared here, which is simply going to be the result of multiplying a2 with b0, or a0 with b2, or a1 with b1. So you get those three terms here. And those three terms can be represented using a summation sign as shown over here. K is being used to represent the index of A and B. So A sub K and B sub 2 minus K. So these individual terms here, three of them, are being represented as a summation here. Now, if you notice, the summation is very similar to the convolution sum that you have. So this is essentially the convolution sum when n equals 2. So for C2, we got the n equals 2, we got C2. So if you now look at it zooming out, if you look at the entire expression here, those coefficients, 5 of them, are essentially the output of the convolution between two inputs with values a2, a1, a0 and b2, b1, b0. So you can view convolution as a polynomial multiplication as well. Now you see it is not one-to-one multiplication here. It is the cross products are also appearing, which is similar to what we see in the discrete convolution of shifting, multiplying, adding, and so on. So this is one more way of you to visualize convolution. This is the bottom left part of the slide over here is essentially validating that the two discrete convolution approaches, one being the polynomial multiplication, the other being the array, they map one on one. Like they are very they are in agreement. All right. Next, we go on to convolution with an impulse. So let's see what happens when you convolve x of t with delta of t and x of n with delta of n. As you can see here, the top portion of this slide is referring to the convolution in continuous time, and the bottom one is for the discrete time. When you convolve any input with an impulse, which can be represented using the convolution integral as negative infinity to infinity, one of the signals here, in this case x of tau, delta of t minus tau, so the impulse shifted by tau, d tau. That's using the convolution integral. This can be written as x of t because that is essentially the sampling property. You're taking x of tau, you're multiplying with an impulse at tau, that will give you x of tau delta of t minus tau, and you are integrating from negative infinity to infinity, which means that the impulse is included in that integration. So it just simply gives you x of t. That's the sampling property we have seen in lecture 3, 4 earlier. So the point to be noted here is, if you convolve anything with an impulse function, you get back the same thing. X of t, any arbitrary function of time convolved with an impulse, you get back the same output, x of t. This can be represented using an input, output, and the system in the middle in a graphical manner as shown below. So what I'll say is x of t goes in, and let us suppose that my impulse response of the system is delta of t. If x of t goes in, and I'm saying that my impulse response h of t is delta of t, then the output is simply going to be x of t, which is what? Which is x of t input convolved with h of t. In this case, it is x of t convolved with delta of t, and we just proved using sampling property that it is x of t. Now, before I go any further, I need to explicitly write that this is an LTI system. Otherwise, none of this matters. Next, we can do the same thing for discrete time. X of n convolved with delta of n can be represented using the convolution sum first, and then when you evaluate x of m and multiply it with delta of n minus m, delta of n minus m is 1 only when n equals m. So I can write this as equals 1 only when n equals m, which means that this summation will evaluate to x of n. In the form of a block diagram that can be represented as x of n going into an LTI discrete system with an impulse response of delta of n. The output will be x of n. There's a question on the chat box. When you convolve, are the bounds always from negative infinity to infinity? Yes. In general, it will be from negative infinity to infinity. Then, as you are using the properties of the signals being convolved, those limits will come down. They will be more very well defined after you start using the properties of x of tau and delta of t minus tau. So the signals themselves should be used to adjust the limits of the integration or summation. But at the beginning, you should start with negative infinity to infinity. All right, let's see here. Okay, so we talked about the impulse response, x of n convolved with it. So that's convolution with an impulse. You get back the same thing, as simple as that. You're absolutely right. We will never have a situation over here where the delta function is not included in the integration. Because it's going from negative infinity to infinity, this impulse will always be included, and this will always be equal to the signal over here. So this is a general property, and it will always apply. In the same case over here, whatever function of goes here, it goes there. All right, let me remove these. I don't want this to lead to any sort of confusion. Okay, let's move on here. How about time reversal property? This is one of the very useful properties for convolution. So we are looking at both the continuous time and the discrete time equivalents of the time reversal property. We have defined C of t as convolution between A of t and B of t. Then the time reversal property says that if you flip A and you flip B and you convolve those two together, it will result in flipping C by the y-axis. So if you convolve, flip A, flip B, convolve, it will result in the flipping of the original output, C. Similarly, this time reversal property can be expressed for discrete time signals. If C of n is equal to A of n convolved with B of n, then if you flip A and you flip B and you convolve those two, the result of that discrete convolution will be the time flipped version of C of n, which is C of minus n. Now, some of these properties can be proved, and we will be proving some of these properties. And some of these properties have been proved and made available to you in the supplemental video lectures. However, I just want to make a generic statement here. All the properties of convolution for both continuous time and discrete time convolution can be traced back to their original definitions, which is the convolution integral and the convolution sum. So all of these properties can be proved. The only thing that you have to do is start using the convolution integral or the convolution sum and then make the required substitutions and manipulations. I will show you some examples, Jason. You will take a look at how about when you flip only one, what happens. Just bear with me for a minute. Now let's move on to the commutative property. The commutative property is laid out for both continuous time and discrete time in the box above. X of t convolved with h of t is the same as h of t convolved with x of t. So the order in which you do the convolution doesn't matter for continuous time as well as for discrete time. X convolved with h is the same as h convolved with x. Now here is the proof. And I will run through this for the case of discrete convolution, and you could apply the same sort of steps for the integration. The proofs will be very similar. As I mentioned, they all start with using the convolution integral or the convolution sum. In this case, because we are doing it for discrete time, they go back to the convolution sum. So let's take a look at y of n. Y of n equals x of n convolved with h of n. That's the output indicated by y of n. The two signals being convolved are x and h respectively, which can be written as a summation or convolution sum as m equals negative infinity to infinity x of m h of n minus m. Now let us define Z as another discrete sequence, which is H convolved with X. So the reverse order. In this case, we are still having that summation m equals negative infinity to infinity. Now, because we are putting h up front, we have h of m multiplied by x of n minus m. Now, our goal will be to show that y of n and z of n are the same for all n. And if we do that, we have proved that convolution is commutative, at least for the discrete case. Now observe that y of n right here which is represented as a convolution sum. Now what we are going to do is we are going to apply a change of variable. So the change of variable is being applied so that now n minus m can be represented using another variable k. So if k is equal to n minus m, then m can be written as n minus k. The limits of the summation need to be adjusted because now you are no longer summing up things with respect to m, you have changed it to k. So when m equals negative infinity, k evaluates to plus infinity. When m equals infinity, k equals negative infinity. If you apply all these change of variable steps to y of n, what is going to happen? The summation sign is going to change such that you have from m equals negative infinity to infinity, now you have k equals infinity to negative infinity. X of m becomes x of n minus k because m is n minus k. And h of k is the result of changing n minus m to k. That's what we defined. Now a little bit of simplification here. So k equals infinity to negative infinity can be written up in the reversed order without any effect to the summation because summation is commutative. H of k can be written up front because multiplication is commutative. Then you can have h of n minus k written up over here. All of this is the same as what we had earlier. So if you see this, z is the same as here. The only change being k instead of m, nothing else. So we can write this as z of n, which proves the commutative property for convolution. Now you go through the same steps. Instead of summations, you will have integrations. You will do the same change of variable. You will do the same adjustment of the limits of the integration. You will go through the same steps and you will be able to prove commutative property for convolution, continuous time convolution. Same steps. Now an extension or the application of commutative property. What happens when you connect systems in cascade? So we have two systems, and I should probably write explicitly that this is LTI, this is LTI, this is LTI, this is LTI. Each of them is individually linear and time invariant. They are expressed in the form of their impulse responses as h1 of t or n, doesn't really matter whether they are continuous time or discrete time. So h1, h2, h2, h1. So the order of those impulse responses is flipped. So in the first case, the top case here, what would be the output of system 1? Well, the output of system 1 would be x convolved with h1. Now, if you take that and go into a linear time invariant system with impulse response h2, what are you going to have for y? Well, you are going to have, first you do x convolved with h1. Now you convolve with h2. Now, because these are commutative, it will be the same output when you switch the two around. Meaning, if the input goes into LTI with impulse response H2, the output is going to be X convolved with H2. Then it goes through a system with impulse response H1. You get the output X convolved with H2, then convolved with H1. And because it is commutative, the cascade connection here is the same output. In other words, if you have multiple systems that are connected in cascade, the order in which those are connected doesn't matter. Can also be written for the sake of finding the overall system impulse response. So if we consider the entire red box as the overall LTI system, then the overall LTI system impulse response in both cases is H1 convolved with H2, which should be the same as H2 convolved with H1. So now you can simply look at it as one system input convolved with that overall system will give you the output Y. This applies for both continuous as well as for discrete cases. Now let's take a look at time shifting property of convolution. First continuous time, then discrete time. For the first case, we have continuous time given that C of t is the result of continuous time convolution between A of t and B of t. Then for any time t1 and for any time t2, this is all real. So these are t1 comma t2 belong to real numbers, set of real numbers. If that is the case, if you shift A by t1 and if you shift B by t2, the result is shifting of the output by the sum of t1 plus t2. Can also be written as t2 goes up front, t1 goes here, t2 goes here, which means that if you consider A convolved with B, no matter where you shift A and B, so if you shift A by t1 and B by t2, it is the same as the convolution output when A was shifted by t2 and B was shifted by t1. And to combine both these into one, it is equivalent to the output getting shifted by the sum of those two time shifts, which is indicated as either this, or you can also write it as C of t minus t1 plus t2. So that's the time shifting property, and we'll see some applications of this in a little bit. For discrete time, same rule. C of n is the convolution, discrete time convolution output of A and B for any integer n1 and n2. So these are integers here. And those are belonging to the real numbers. Next, if you shift A by n1 and B by n2, it is the same as shifting A by n2 and B by n1 in terms of the convolution output. C of n gets shifted by the sum of those two time shifts, n1 and n2. Again, this can also be written as C of n minus n1 plus n2. All right, so let's ask a few questions here in order to check our understanding. X of t convolved with delta of t, what is the output? We just proved it. Any signal that convolves with an impulse gets back the same signal, x of t. What's next? X of t convolved with delta of t minus t0. Using the time shift property that we just laid out, x of t minus t0. So if delta of, because the impulse shifted by t0, the output gets shifted by t0. This is using the time shift property that we just laid out. How about the last one? Discrete x of n minus n0. You're absolutely right. All right, so we have answered a few questions here as quick examples of application of time shift property and the convolution with the impulse property. Next, we are going to be looking at some more interesting properties of convolution. This is the symmetry property. Well, there are multiple of them. So they are symmetry properties. We'll start with even function convolved with an even function. The claim is that if you convolve two even functions, the result is also an even function. So let us try to validate that a little bit by taking a of t, which is an even function here. It is symmetric about the vertical axis. And we are trying to convolve this with another rectangle here, b of t, also symmetric about y-axis, so also even. These are for continuous time, but this property applies for even discrete time. So when you convolve these two, my claim is that this is going to be like a trapezoid looking waveform. Now, I was able to write this directly. Believe it or not, I was able to write this convolution output directly. So before I go any further, I want to show you guys a few tricks. As long as you are convolving rectangles, you should be able to do that relatively quickly. And the reason why you can do that very quickly is because a rectangle convolved with a rectangle will always result in a linearly increasing function or a linearly decreasing function, or it might be a constant when the two rectangles, one rectangle is completely inside the other. So it will either be a trapezoid or it will be a triangle. It will be a triangle if those two rectangles exactly overlap with each other in terms of their timing. So if they start and end at the same time, then it will be a triangle output. But if they start and end at different times, the way it is shown here, it will be a trapezoid. So I want to start talking about how was I able to write this output so fast. It is about trying to figure out the lower limit of the output, the upper limit of the output, the height of the trapezoid, and where it stops increasing and where it stops decreasing. If I find out those 1, 2, 3, 4, 5 values, I'm done. I will highlight those 5 values here. Let's see. I will highlight this in yellow, this in blue, and this in pink. So let's see how they are related to the two rectangles. The lower limit, -7, is essentially obtained by adding up the lower limits on the two signals, -3, -4. Similarly, on the positive, you just add up 3 and 4, you get 7. Done. How about 24? How do I know that the height is going to be 24? Because that is suggesting that one of these rectangles is completely inside the other. Well, this one is narrower. The first one, A of t, is narrower than the second one. So A of t is going to be completely inside B of t. And when it is, what is going to be the product of those two signals? Followed by the integration for 6 time units. When you multiply 2 and 2, what do you get? 4. And then you integrate that by for 6 time units, because this is 6, because that's the smaller rectangle completely inside. So that gives you the 24 which we have over here. Now we talked about the low 7, -7, we talked about 24. How about -1 and 1? Well, as this guy is completely inside this, for how long is it going to be completely inside this? It is going to be inside that for 2 seconds. Why? Or 2 time units. Why? Because the difference between these two is 8 minus 6, 2 time units. So that's when it is going to be completely inside. And it is going to start being inside as soon as you go in 6 time steps. So that's -7 all the way to -1. And it will stay there inside for 2 time units. And then for 6 time units, it will be coming out on the other side linearly. Why linearly? Because constant multiplied by constant integrated will give you a linear function. So I hope that that discussion was helpful, and you are able to take this discussion and be able to sketch the convolution output for rectangles very, very quickly, but just by inspection almost. All right, let me erase these. Do I need to erase this? No, I can leave it as is. So A convolved with B, even signal A, we know that. How? Just visually, right? If you look at it, it is symmetric about the y-axis. B is also even. When you convolve two signals that are even, you got even output C of t. And if this rule breaks, you know something has gone wrong somewhere. Mathematically, some mistake has been done. Now, if this is the property, even convolved with even is even, for a later reference, I'm also going to sketch the derivative of C of t. So this trapezoid, I'm defining the derivative of this trapezoid with respect to time, and I'm sketching that over here. Linearly increases from -7 to -1. So that will correspond to a slope of 4, positive 4, from -7 to -1. Between -1 and 1, the slope is 0. From 1 to 7, the slope is -4. That corresponds to the line, the linear function going down with time from 1 to 7 seconds. And you can see the slope is -4 there. Change in y is 24, change in x is 6. So for a later reference, I'm going to preserve this. Moving on. So even convolved with even is another even function. How about odd convolve with even? Let us try to find that out. A of t, we have taken A of t and simply differentiated that with respect to time. So if I show you A of t here, it is simply going up at -3 and coming down at 3. And it goes up and down 2 levels in amplitude. So finding the derivative of A of t will be 2 pointing up. So that's the weight of the impulse is 2 at time -3. And the weight of the impulse is -2 at time 3. So that's the derivative of A of t. And as you can see, it is going to be an odd function because it is symmetric about the origin. Now, when you convolve this with b of t is the same rectangle from -4 to 4 with the height of 2, same one as before. When you convolve that with that, I want to be able to write the output directly. Now, I know that I can use additivity in LTI systems. So if I can use additivity, I can convolve this impulse with the rectangle and then this impulse with the same rectangle. So I can do this in 2 steps and then later on add the output together. So when I convolve the first impulse all the way on the left with b of t, what do I get? It will start at, let's see here, it will start at -7 and it will end at -3 plus 4, 1. And what will be the height of that rectangle? It will be 2 times 2, 4. I'm using the property of convolution with impulse over here. So the red triangle in C of t is simply the convolution of the left impulse with b of t. Similarly, I can do the one on the right. Time 3 plus and minus 4. That will give me -1 all the way to 7. What is going to be the height of that rectangle? -2 times 2. So -4. So it's going down. So I've got the output of C of t, the two pieces. I can just add them together. When I add them together, I have +4 between -7 and -1. Between -1 and 1, they cancel out. 4 minus 4. And then from 1 to 7, I have -4. So that would be my output for C of t. And as you can see, this is symmetric about the origin, which means this is going to be odd. Odd convolved with even is odd. Now for the third property, which we have odd convolved with another odd signal, the claim is that it is going to result in an even signal. And for this, let us prove it using a convolution integral. So you can use the same proving technique for the previous two properties. I'm just using the third one and providing the proof for that. So let's see. A of t is negative a of minus t. Why is that? Because I said a of t is odd. B of t can be written as negative b of minus t. Why? Because it is also odd. So I'm considering that the two signals I have are odd. So by definition of odd, a of t should be the same as negative a of minus t. So a flip about x and y axes for both a and b. Now, our goal is to show that a convolved with b, which is C of t, is going to obey this condition, C of t equal to C of negative t, which means that it is an even function. So let us start with C of t, defining C of t as a convolved with b, which can be written as a convolution integral as -∞ to infinity a of tau b of t minus tau d tau. We could have also written it in the other, because convolution is commutative, we could have written it as b of tau a of t minus tau d tau as well. But we are choosing to write it in this form here. Then let us try to form C of minus t. So we are going to go from C of t to C of minus t. And we can do that by changing the variable t to negative t. Let's do that. -∞ to infinity remains as is, right? Oh, sorry. -∞ to infinity remains as is. A of tau remains as is. Now b of t minus tau becomes b of minus t minus tau, because we have gone from t to negative t, because we are forming c of negative t. D tau remains as is. Now, using the properties of a and b and the fact that they are odd, I can write a of tau as negative a of minus tau and b of negative t minus tau as negative b t plus tau, because I can pull out a negative 1 here and then use the odd property. Multiplying it out, the negative signs cancel out, the integration remains as is, negative infinity to infinity. Instead of a of tau, I have a of minus tau. Instead of b of minus t minus tau, I have b of t plus tau from here. The negative signs cancelled out for the amplitude of a and b. Let's do a quick change of variable, because there is one more step lacking. Let a new variable lambda be negative tau. So c of minus t is going to be negative infinity to negative infinity, because we have changed the variable. So instead of d tau, we will have d of minus lambda. The limits of the integration get flipped. Instead of a of minus tau, now you have a of lambda. And instead of b of t plus tau, you have t minus lambda. Simplify one step further. A of lambda can be written as a new variable a of tau. B of t minus lambda can be written as a new variable b of t minus tau. D lambda can be written as simply d tau, because I've changed that negative sign to change the limits from negative infinity to infinity. This circling back is the same as c of t, because that's did I write c of t somewhere? Yes, I did. So if you compare this and this, they are the same. Let's see here. There's a question on the chat box. I'm not sure. Let me check whether it is pointing to this. Reagan, is this your question over here or about this one? So about the last step here, no. Right, lambda is negative tau, yes. All right, let's see here. Let's see. Next step is going to be, okay, so we proved this property, the third one. Odd convolved with odd is even. Let's do an example here. Lot of impulses. I really like that, because it makes the convolution extremely simple to go through. Just as an exercise, let us write a of t and b of t in the form of in terms of impulses. Let me use red for that. So a of t, how can I write that in terms of impulses? I can write that as negative delta of t plus 1 plus delta of t minus 1. Those are the two impulses for a of t. It is odd because it is symmetric about the origin. Now b of t. B of t can be written in the form of impulses as, it's the same one. So negative delta of t plus 1 plus delta of t minus 1. Same as a of t in this case. Also odd because it is symmetric about the origin. So what happens when you convolve these two? Well, we can go piece by piece. Let us focus on, let's see here, maybe this. If you convolve those two elements, what do you get? An impulse negative 1 convolved with negative 1. What will be the height? What will be the times? The height will be -1 times -1, so 2. Sorry, -1 times -1, so 1. The time will be -1 plus -1, so -2. So let me point that as, let's see here, 1, 2, pointing up right there. And the limits are going to be what? This is going to be at time 2, and this, the weight is going to be 1. So those are the negative delta t plus 1, those two terms. Next, let us use a different color here, and let's do the outer two. What are those two going to result in? There is an impulse at 1, there is also an impulse at 1. So 1 times 1, amplitude is, or I shouldn't say amplitude, the weight of that impulse is going to be 1, and it is going to be located at 2. You meant to write -2. Yes, you are absolutely right. And at 1, 2, here is 2. And for this guy, the result is also going to be positive, and it is going to be a height of 1 here. Now they are going to be two cross product terms. Negative impulse with a, so it is going to be, let's see, this guy with this guy, and this guy with this guy. So for those, the amplitude is going to be -1, and the location is going to be 1 minus 1, so 0. So those will be, it will be pointing down with a weight of -2. And if you notice, this is an even signal. It is symmetric about the origin. It is symmetric about the y-axis. Let me fill the information here. This is 1. Yeah, done. So we have done this graphically. Actually, you could have done this even analytically by convolving one impulse with the other, and then using the convolution with impulse property to write out 4 terms. You will be able to combine 2 of them into this particular red impulse here. So you can do that individually as well, writing it out in the expression form. All right, odd, odd, even. First we proved it. Next we looked at an example. Now let's talk about the derivative property. If you differentiate the convolution output of A convolved with B, the claim is that it is the same as A convolved with the derivative of B, which is the same as derivative of A convolved with B. All the same. If you differentiate both signals, or if you differentiate one of them, it is the same. Now, this has been shown in symmetry A and B. Where did we show this? Now, if you look at this, symmetry A and B, let's try to take a look at what those are. Symmetry A, so B was here, where we differentiated A of t and convolved with B of t, and we got C of t there. And if you notice, this is exactly the same as differentiating C of t. So first you do the convolution, then you differentiate C of t. So we have kind of proved this. So it's first you convolve, then you differentiate, you get that. Or in property B, we differentiate A of t, so one of the signals, and then you convolve, you get C of t, which is the same as before. So that essentially is a validation of my derivative property, which I describe over here. So this was, let's see, the whole thing was derivative of c of t with respect to time. This was symmetry A. And then we did this in symmetry B. So you can take a look at those two slides to take a look at what we did. And the claim is that even if you differentiate B, leave A as is, you will get the same result. And this can be quickly shown with the given A, B signals. All right, let's go to the distributive property. Now, distributive property is one of my favorites because you can really take advantage of the properties, this property, for a lot of convolutions. So let's take a look at the property, then we'll take a look at an example. So the statement of the distributive property is, if you have A of t convolved with the sum of B of t and C of t, it is the same as convolving A with B and adding it up to convolving A and C. That is for continuous time signals. You can apply the same distributive property for discrete time signals. A of n convolved with the sum of B and C is the same as A convolved with B plus A convolved with C. This can be used to convolve these two signals as an example. And you will really see the advantage of using this property for this example here. So my first attempt is going to be able to write B of t in terms of A of t. A of t is simply what? You have a gate function, right? G of t, gate function there. Opens the gate at 0, closes the gate at 1, height is 1. So A is essentially gate function G of t in terms of our standard or the common signals. So let's try to write B of t in terms of A of t. And I can do that if I simply break up B of t into 3 pieces. So let me identify them as 1, 2, and 3. So let's write B of t in terms of A of t. What is B of t? For the first piece, I simply have A of t. That's the first piece. For the second piece, I need to multiply the amplitude by 2, and I also need to shift by 1. And for the third piece, amplitude stays the same, but I need to shift by 2. So using the time shifting property, essentially, I have written out B of t in terms of A of t. You will see the reason why in just a bit. Now, when we are convolving A and B, and I was able to write B in terms of A, all we really need is A convolved with A. So if we have A convolved with A, we can use the distributive property to write the entire convolution result. So what is A convolved with A? So let us define A convolved with A as a new signal, say M of t. We only need A of t convolved with A of t. So let's define this as M of t. So using the skills that I had discussed earlier about convolving rectangles, are you guys able to tell me the result here? A convolved with A. When does it start? When does it end? Is it going to be a triangle or a trapezoid? It is A with A, so it is going to be a triangle. So let me draw a triangle here, and then you guys can probably help me figuring out the limits. when does it start and when does it stop. Starts at 0, ends at 4. A convolved with A. So starting at 0 is good because it is going to be, let's see, 0 plus 0, right? So 0 plus 0 is 0, you're done. Like that's good. Ends at 2, right? Ends at 2 because you have 1 convolved with the same A of t again, you got 1 plus 1, you got 2. So let me write down 2 over here. Can I put a 1 in the middle here? So think about this. Can I put a 1 in the middle? It is symmetric. If it is symmetric about this here, it is going to be symmetric in general. And it has even symmetry. So the output also should have even symmetry. And it has to be even symmetry about a new point, which is corresponding to half plus half, which is 1. So using the symmetry property, you can say that it should be symmetric about a vertical line at 1. Next, what is the height? Height is going to be the answer in the chat box is amplitude of 1. So let's try to validate if this 1, if it is correct or not. Well, all I have to do is multiply 1 with 1 and integrate for 1 time. So 1 times 1 times 1 is 1. Good. So height is okay. That's it. If you have m of t, it helps our example tremendously over here, because what I can do is I can say, if I say that, let's see, c of t is, say, a of t convolved with b of t, I can write this as a of t convolved with b of t can be written in a of t terms, a plus 2 a of t minus 1 plus a of t minus 2, which can be written as a of t convolved with a of t plus 2 a of t convolved with a of t minus 1. I hope you see where this is going. A of t convolved with a of t minus 2, which is simply m of t plus 2 m of t minus 1 plus m of t minus 2. So I use the distributive property and then I use the time shifting property to write these two statements. And that is what I'm going to box over here, because that will allow me to sketch things very quickly. I need m of t. I already have that plotted. I need to add 2 times m of t minus 1. And then I also need to add m of t minus 2. So all those 3 pieces, one of them we already have. But in general, you can break that into 3 triangles. Those have been sketched over here individually. So the first one, let's say, is m of t. This guy is 2 times m of t minus 1. And this guy is m of t minus 2. Now when you add everything, what are you going to get? From time 0 to 1, you only have things that are increasing with a slope of 1. So you get that until 1. Between 1 and 2, you have one guy increasing with a slope of 2, one guy going down with a slope of 1. Effectively, it is going up by 1 again. So it continues to move up until 2. At 2, you have something going down with a slope of 2, but one which is going up with a slope of 1, so you're effectively going down by a slope of 1. And from 3 to 4, you only have something going down by a slope of 1. So even in total, it is simply a triangle starting at 0, ending at 4, in the middle it is 2, and the height is 2. This is C of t. Questions about this example? All right, let's move on here. Now we can look at the commutative property in terms of cascade connections between LTI systems. And similarly, we can look at distributive property in terms of parallel connections between LTI systems. So if you have two systems over here, say they're all LTI. So let me just put LTI here, and the overall system will be LTI because it comprises of things that are LTI and a summer. You have two paths here. This is parallel connection. X goes through H here and X goes through H2 here. So the distributive property says that X convolved with H plus H2, H1 plus H2 is the same as X convolved with H1 plus X convolved with H2. And you can apply that to a parallel connection as shown by evaluating the outputs on each side. So what is going to be the output of the LTI system with impulse response H1? It is simply going to be X convolved with H1. Over here you get X convolved with H2, and that is getting added up over there. So you get Y, which is X convolved with, H1 plus X convolved with H2, which is using the property X convolved with H1 plus H2, which means that you can treat parallel systems that are getting added up later as a system with impulse response H1 plus H2. So the system impulse response here is simply the addition of the impulse responses H1 and H2. So now you can use those properties and apply that to cascade and parallel connections of LTI systems. Let us talk more about the properties of LTI systems here. The next property of LTI systems is memoryless systems. Systems that do not have memory. An LTI system is considered to be memoryless if and only if the impulse response of discrete system is some scalars C multiplied by delta of n, or for a continuous time system h of t, the impulse response of that system is some scalar C multiplied by an impulse. What does that mean? That means that I'm saying a system is memoryless only if when its impulse response is defined at time 0. At all the other times, it has to be 0. H of t is non-zero only at time 0. So h of t should be some c, 5 delta of t, negative 2 delta of t, some scalar delta of t, or in discrete times, c delta of n. If this is not the case, then I cannot call the system memoryless. Now, if you go back and think about the same definition, memoryless systems that we defined earlier, It was in lecture 5 when we defined memoryless system as output signal depends only on present inputs. We said if y of 0 depends on x of 0, y of 1 depends on x of 1, y of -1 depends on x of -1, and so on for all time belonging to the set of real numbers. Only then we can say it is memoryless. So now we have gone away from that definition of memoryless being the relationship between output and input, and now we are introducing the relationship of, sorry, not relationship, we are introducing the we are adjusting the definition of memoryless systems to its impulse response. So you can find out memoryless using the definition in lecture 5 or by looking at its impulse response. Both ways should be the same, and they are the same once we actually prove that they are the same. And we can prove this by looking at the definition of the convolution sum. So y of n, the output of this system, I don't know whether it is memoryless or memory with memory right now. I'm claiming that it is memoryless, but y of n, I can write that y of n in terms of a convolution sum this way. I can say it is summation m equals -infinity to infinity x of m h of n minus m. And I proved that convolution is commutative, so I should be able to write this summation as summation m equals -infinity to infinity h of m x of n minus m, because convolution is commutative. Now I can break this convolution or summation into 3 different terms. The first term is when m goes from -infinity to -1. The second term is when m is 0. The last term is when m is 1 to infinity. And as you can see here, x of n minus m for m between -infinity to -1, those are all future inputs. Similarly, for the last term over here, x of n minus m for m going from 1 to infinity, those are all past inputs. So if the memoryless system doesn't depend on future inputs and past inputs, then those summations should contribute nothing. Which means even if the input is there, my system should take care of cancelling that out to a 0. So the only term that should be left is h of 0 multiplied by x of 0, which can be written as c delta of n, because h of 0 multiplied by x of 0 is input evaluated at time 0, impulse response evaluated at time 0. So for an LTI system to be memoryless, h of n should be 0 for all n other than 0. It should be non-zero only when n is 0. These two statements can be represented in one expression using h of n equals some scalar c multiplied by delta of n. So by using the definition of convolution sum and by using the properties of future inputs and past inputs, we have proved that this statement y of t0 depends on x of t0 is the same as saying h of t is c delta of t. Or for discrete time, h of n is the same as h of n is equal to c delta of n. Questions about this? Let's move forward here. On the same lines, we can talk about causality and stability as well. Notice here what we are trying to do is we are trying to go away from output-input relationships to commenting about the impulse responses for those systems. For causality, an LTI system is considered causal if and only if the impulse response of that system is 0 for n less than 0. So it doesn't have any non-zero value for negative time, both for discrete as well as for continuous. H of t is 0 for time less than 0. So if these two are satisfied, or if this condition is satisfied, then the system is considered to be linear and causal. This particular linear time invariant system is considered to be causal system. And we can trace it back to the same way. We defined causal system in lecture 5 as causality is when the output signal depends on present or past inputs. In other words, we said the output at any time t doesn't depend on input at time larger than t. So it cannot depend on time that hasn't happened yet. We can tie up these two relationships between causality output input relationship and its impulse response by using the convolution sum again. Y of n can be expressed as a convolution sum here, m equals negative infinity to infinity. X of m, h of n minus m can also be written by using the commutative property of convolution as m equals negative infinity, summation m equals negative infinity to infinity, h of m, x of n minus m. Break it up into two pieces here. We don't need to go three pieces. Two pieces are enough. One is the summation going from negative infinity to negative 1, the other going from 0 to infinity. All these are going to be future inputs because x of n minus of minus 1. So x of n plus 1, x of n plus 2, x of n plus 3. Those are all future inputs. And the second term over here is present, that is when m equals 0. And then past inputs when m is greater than 0. Notice over here, these are discrete signals. So the variables being used are integers here. So if it doesn't depend on future inputs, only depends on present and past inputs, that means that this term needs to evaluate to 0. And this can evaluate to 0 if there is no element in the impulse response for negative time, which can be written as, for LTI system to be causal, h of n should be 0 for n less than 0. Now, one question that I get when I talk about these things is, how do we know h should be 0? Why not x should be 0? Right? If this is 0, the product and the sum should be 0. So why are you saying that h of n should be 0? Why not talk about the input being 0? Well, the answer to that is this. We are talking about a system property, not a signal property. Input x is in the control of the person using the system. So I can provide an input at time 0, plus 2, minus 1 at any time. That is in my control. But the property of the system, in order for it to be a causal one, should be dictated by its impulse response or by how the output is related to the input. Output-input relationship we did earlier. Now we are focusing on the impulse response. So I cannot enforce that this should be 0 because that's an input. It's in the user control. But I can enforce H for causal systems or for memoryless systems, because it's a property of a system, not the signal. All right, let's see. Stability. We defined bounded input, bounded output stable systems. We can apply the same conversation. Instead of looking at the output-input relationship, we can look at its impulse response. A different condition, but now based on impulse response. For an LTI system to be bounded input, bounded output, we need to satisfy these conditions. The left one is for discrete time system, the right one is for the continuous time signal. continuous time system. What does it say? It says that if you take all the values of the impulse response, take the absolute of all the values in the impulse response. So those are going to be all positive values, right? Once you take absolute, those are going to be all positive values. And if you add up all the positive values inside that h of n from n equals negative infinity to infinity, if that is less than infinity, that means that it is a bounded input, bounded output stable system. Similarly, for continuous time systems, you can say if you take h of t, the impulse response of the LTI system, take the absolute of that, which means that you have flipped all the negative parts to the positive side, and you integrate for all time. And if you get that to be a finite result, less than infinity, then you can say that it is a bounded input, bounded output stable system. Again, goes back to the conditions of output versus input. If you have a bound on the input, then the output should be bounded. It is related to the same condition that we have described over here in terms of its impulse response. So the above conditions are sufficient conditions for bounded input, bounded output stability. So you don't need not go any further and evaluate for each input what is the output. As long as these are satisfied, it is a bounded input, bounded output stable system. So these are sufficient conditions. These are not just necessary conditions. The inverse of a LTI system. This is a very interesting topic. If I know the impulse response of a system, H, can I find out the inverse of that system? Something that does the exact opposite. So the inverse of the LTI system, H, we are defining it as H subscript INV that satisfies h of n convolve with h inverse of n should give you an impulse. If it does, then it is h of inverse is the inverse of the system. For continuous time, this can be written as h of t convolve with h inverse of t should equal impulse. If it is, then you can say h subscript inv is the inverse of h of n or h of t. I get back what I have if I go through H inverse, is essentially what this means. So consider this. X of n is the input. If it goes through an LTI system with impulse response H of n, I get Y of n. Y of n we know Y of n can be written as X convolved with H. And if I now go into another LTI system with an impulse response H subscript INV, if I get back my X, then this will be considered the inverse. And what is this? This is simply X convolved with H convolved with H inverse, which is what? X convolved with delta is X. So if that is true, then we can consider H inverse to be the inverse of H. Over here, the system transfer function can be written as H of n convolved with H inverse of n. I shouldn't say transfer function. I should say the impulse response of the overall system should be written as H of n convolved with H inverse of n, which is simply delta of n. So how can this be of use? Well, think about a system that is giving you some trouble, meaning it is adding some noise. So what you can do is you can put another system in front of it, and whatever input without the noise goes in, when it comes out, you know what is the inverse of that system. And once you know the inverse of the system, that's it. Now you don't need to do any experimentation. You now know what will cancel out noise for that LTI system. So this can be of a lot of use, the inverse of the system, in very real situations. All right. Let's start talking about the step response. We were so focused on the impulse response, but I also said that we can describe completely, we can characterize the LTI system using its step response. So let us try to formally write the relationship between step response and the impulse response. So over here we have u of t, a unit step, goes into an LTI system with impulse response h of t. The output is going to be y step. Step goes in, step response comes out. We have defined the LTI system impulse response as h of t. Now y step of t, which is the output when the input is u of t, step response, can be written using the convolution integral. Integration negative infinity to infinity u of tau h of t minus tau d tau. So it's the same convolution integral. Instead of x of tau, we have u of tau because the input is u of t. Because we know u of tau is 0 for tau less than 0, we can modify the lower limit of that integration to be 0. So now the integration limits are 0 to infinity h of t minus tau d tau. Let us apply a change of variable because we want it in the form of h of x dx. Right now it is in the form of h of t minus tau d tau. So we can do a change of variable quickly. Instead t of t minus tau, we change the variable to v. So negative d tau will be dv or d tau will be negative dv. At tau equals 0, the lower limit, v will be t. Tau equals infinity, the upper limit of the integration, v will be infinity. Substitute all of this into the equation over there to get y step of t equals negative. The integration is going from 0 to infinity becomes t to infinity. Instead of h of t minus tau, you have h of v, d tau becomes dv. Actually, d tau became negative dv, we pulled out the negative up front. This can be simplified to be written as y step of t is integration negative infinity to t h of v hv dv. So if you integrate the impulse response of the system, you get back the step response of the system. In other words, y step of t is the integral of h of t. And consequently, if you differentiate both sides, you have h of t, the impulse response of the system, which can be written as derivative of y step of t with respect to time. So differentiate step response, you get impulse response. You integrate impulse response, you get step response. So the relationship between impulse response and the step response is of integration and differentiation. We can do the same analysis for discrete time LTI systems. So consider y step of n, which is the step response of the discrete time system when the input is u of n, which is u of n convolved with h of n, its own impulse response, h of n. This can be written in the form of a convolution sum because now we are dealing with discrete time system. Summation m equals negative infinity to infinity h of m u of n minus m. U of n minus m can now be leveraged because now we know that it will help us reduce the limits of the summation. U of n minus m is 0 when n is less than m, is 1 when n is greater than or equal to m. So if we use that, we can write y step of n as simply m equals negative infinity to n h of m. So sum up all the elements in the impulse response to get y step until that time. And similarly, I can rearrange this to write the impulse response as the first difference of the step response. H of n is y step of n minus y step of n minus 1, which is related to the same definition over here. You can prove that by writing y step of n. You can replace n with n minus 1, write an expression for y step of n minus 1. You get two elements that you need to be subtracted on the right hand side, which will get back h of n. So take the difference or the derivative to get impulse response. Add things up to get the step response, or accumulate things to get the step response. Now, this is the last thing I want to talk about today, which is to relate some of these impulse response and step response things to circuits. So if the question was find the impulse response of the following circuit, in this case you have a RC circuit. We know it's a low pass filter. We know this is going to charge up the capacitor and so on. And then once you remove the voltage, it is going to start discharging. All those properties can be viewed through the lens of impulse response and the step response and convolution. As long as I can assume that this RC network is a linear time invariant system. So I'm going to do this example assuming that this RC circuit is linear time invariant. I'm going to represent the input voltage as x of t. I'm going to express my output voltage as y of t. I'm expressing the current through the resistor and the capacitor as small I. It is going to be a function of time. For the sake of simple math, I've made R as 1 ohm, capacitor as 1 farad. First, I'm going to write the ODE, ordinary differential equation, for this circuit. The current through the capacitor, is related to the voltage across the capacitor by using a differential equation. I equals C dV by dt, which can be written in this case as I equals C is 1 dV by dt. So in this case, the voltage across the capacitor is y of t. So I should be able to write dy of t by dt. Next, when you apply KVL, Kirchhoff's voltage law, to this loop, sum of voltages across a loop should be 0. Algebraic sum of voltages across the loop should be 0. You have x of t here, you have y of t there, you have I times 1 over there. So x should be equal to I times 1 or I plus y. So if you combine these two statements, you should be able to write this ODE. X of t equals y of t plus dy by dt. Now let the input x of t be u of t. Because we are not directly going to impulse response, let's start with the step response and then try to differentiate the step response to get the impulse response. So x of t is u of t. What would be y of t? Y of t will be y step of t in that case. Input is step, output will be step response. So if you substitute these conditions in the input-output relationship of the RC circuit, what do you get? For input, you have u of t. For y of t, you have y step, derivative of y step, because of this. I'm going to assume that the initial condition is 0, which means that the voltage across that capacitor at time 0 is 0. This will help find the integration constant later on. So once I have this equation here, I will multiply by e raised to t throughout. Why am I doing this? I'm doing this in order to solve the ordinary differential equation. Because when I multiply by e raised to t, I have e raised to t y step of t, which is due to that term there, plus e raised to t d y step of t divided by dt, which is because of that step, because of that term there. And the right hand side is simply e raised to t u of t. I'm not writing u of t explicitly because I'll adjust the times later on. What is my left hand side over here? My left hand side over here is e to the x times y of t. So some function multiplied by another function, e to the t multiplied by a function plus e to the t multiplied by the derivative of that function. We know from calculus classes or differential equation classes that this can be combined into writing that as derivative of the product of e to the t multiplied by y step of t. So now when you integrate both sides, what do you have? When you integrate this guy, the derivative cancels out, you get e to the t y step of t. The right hand side, I need to integrate e to the t, which should be very straightforward. You get e to the t plus some integration constant c. Using the initial condition that I laid out earlier, I should be able to find out the integration constant. So if you substitute the initial condition, you substitute 0 there, and you substitute 0 there, what do you have? Oh, you substitute 0 there as well. 1 times y step of 0, which is 0, right? So all of that evaluates to 0, and this guy evaluates to 1. So c plus 1 equals 0, which means c equals -1. Now combining all these statements, you can write e raised to t y step of t equals e to the t minus 1, which is that is essentially c there that we evaluated just now, the constant. E raised to t appears here, e raised to t appears here, so you can combine them to write y step of t, and you can introduce back your unit step, because now you can say time less than 0 it is 0, time greater than 0 it becomes a 1 here, multiplied by 1 here. So you by combining by rearranging the terms here, you can write y step of t as 1 minus e to the negative t u of t. Differentiate y step, you get impulse response. So differentiating this will require differentiating that, which is e to the negative t u of t. Which means now, you see this, an impulse goes in to an RC, you get back. So what is going to happen is going to charge and discharge. So that's that, e to the minus t u of t. Or if step were to go in to the same RC network, you get back a step. So you get that. So this equation here is that equation there. So by using differential equations, by using some circuit techniques, in this case we used Kirchhoff's voltage law, we were able to find the impulse response of this RC network. All right, I went a bit longer than I wanted, but I'll stop the recording here.